Hi guys, welcome to our channel of Sciences and Mathematics. Today we're going to deal with a branch of physics that goes by the name kinematics. Now kinematics is a study of a branch of physics that deals with the study of motion. Now in this particular subject we are going to deal with different aspects of course pertaining to the definition of specific terms. But we're going also to look at the graphing methods which are being used in describing these aspects of motion. Again, we're going to see different equations which of course are being referred to kinematics equations, which will be used there and henceforth in describing the motion of these particular objects. Now, and different aspects of course of the subject of kinematics. So in that case, without further ado, thank you and welcome. So as we have said, we are going to look at a branch of physics that deals with motion, which goes by the name kinematics. So in that case, as I've said, kinematics is a branch of physics that deals with that entails the study of motion. And this branch of motion, as I've said, of kinematics, the branch of physics that is kinematics that deals with start of motion, of course, we are going to encounter different terms which we need to define so that whenever we mention those terms, we'll be aware of the kind of information that we are referring to. So these different terms are going to be used maybe interchangeably, or some of them might be used in order to denote maybe an aspect. But we are going to look at specific classifications that is going to assist us differentiate these terms, whether they fall under one category or another. So this specific classification that is the correct spelling. We're going to look at specific classifications which basically entails the concept of scalars and vectors, because the terms we are going to mention will of course be falling under these two categories. Of course, if we say something that is a scalar and another one is a vector, they have different properties in a sense that a scalar by definition is a quantity that has got magnitude, but for vectors they only possess magnitude and direction, of course, which is going to affect the properties of these specific terms that we're going to mention. So in that case, whenever I mention a term, I'm going to give it a reference whether it is a scalar or a vector quantity. So in that case, we'll just go and look at these specific terms, and then let me mention whether they fall under the category of a scalar or a vector quantity. So in that case, let's look at these terms that are used under kinematics. So now before we look at that, of course we have defined kinematics as a branch of physics that deals with the study of motion. And of course we can just maybe expand that definition a little bit before we go ahead and say that kinematics can be a study of motion of mechanical points, bodies and systems. So this is a study of motion. It's a study of motion of mechanical points. Study of motion of mechanical points, bodies and systems. Without considering the physical properties, and forces acting on them. So that is the broader definition of the term. As we said that it's a study of, it's a branch of physics that deals with the study of motion, we can as well expand this one to a second definition, which is much broader, and say that kinematics is the study of motion of mechanical points, bodies, and systems without considering their physical properties and the forces that is acting on them. Now, in that case, under the terms that we're going to talk about, of course, these are going to describe different aspects of kinetics, which include some expressions and equations which we are going to mention later in this discussion. So for that case, we'll just define the terms. The first one is position. Position, of course, this is a... Now, position, when we are talking about position in kinematics, it is given by the initial x, can be represented by the initial x, and this one denotes where an object is located. So when we shall be talking about the position, we refer to where an object is located. And then we shall talk about distance. Now in this case, the distance, as I said before, so it is denoted by the letter D. We shall use the letter, not specifically, this is not a standard format for denoting this, but in our case, we shall denote distance using the letter D. Now, distance refers to how far you have traveled, regardless of direction. So this is how far one travels, regardless of direction. So that is for distance D, implying how far one travels, regardless of the direction of travel. So we shall go to a third term, which is the displacement. Now for distance is a scalar quantity. I said I will be measuring whether it's a scalar or a vector. So for that case, distance is a scalar quantity. I just put an S in front of this to denote that it's a scalar quantity. So this third term is displacement. Now in that case, we shall indicate the displacement by delta x. Now displacement is of course a vector quantity, which means it has got magnitude and direction. So at the end of the statement, we shall denote that. So displacement is where you are in relation to where you started from. So this one implies where one is with respect to the starting point. So that one refers to displacement. It is where one is with respect to the starting point, or where one started from. That is displacement. And in this case, of course, the displacement is a vector quantity. So I denote it by V. So as we have seen, these are some of the terms that we have defined, and we're just going to continue finding other terms until we exhaust, of course, the ones which are going to be relevant in our discussion for today. So as we have defined displacement, let's look at another term known as speed. So speed in this case is denoted by letter V. We shall denote speed by the letter V. And it is a scalar quantity, and it refers to how fast one goes. So speed refers to how fast one goes. And in this case, speed is a scalar quantity. So the next term that we're going to look at is velocity. Now velocity is as well, we're going to denote the velocity as well as v, but we're going to differentiate between the two, between speed and velocity. So in that case, velocity is how fast one moves and which way, which of course is the rate at which position changes. So in this case, velocity is different from scalar in a sense that it is going to give, of course, how fast and which way one moves. So it's going to give direction. So it does magnitude and direction. So in that case, we can say that how fast one moves and we can just say which way. Of course, it's not a formal, just giving it in a simpler way so that we can be able to understand. So velocity refers to how fast one moves and which way. So which means it's a definition that is giving quantity, magnitude, and direction. So this particular quantity is a vector quantity. So in that case, there is a vector. So velocity, as we have said, is the rate at which position changes. As a second definition, you can say that it's the rate at which position changes. And when we are talking about the term rate, we introduce an aspect of time. So in that case, we are going to give the rate at which position changes. So in this case, we talked about position that we denoted as x. Now, because of the aspect of change, then we are going to give it delta x over delta t. The rate that is implying the change in displacement over time, of course. Then we are going to look at the term average speed. Average speed generally refers to, okay, let's do away with this. Average speed. Average speed is denoted as v per v that has got a bar over there. So it's given by the distance over time. Remember we talked about velocity and speed. So this is average speed, distance over time. And we say that distance, how far one travels regardless of direction. So which means distance is a scalar quantity. And therefore, for that case, this particular aspect is going to be a scalar quantity, which is average speed is a scalar quantity. So then we shall look at the last one, which is acceleration. Look at the last term, acceleration, which is we're going to denote by the letter small lowercase a. This refers to how fast you speed up, slow down, or change direction. Generally refers to the rate at which velocity changes. So we can say that it's the rate at which velocity changes. So in actual sense, we can give it in an expression form that acceleration is equals change in velocity over change in time. So that's just an expression for defining, or an equation for defining acceleration. And in that case, it has got direction, so we are going to see that this also is a vector quantity. And that forms a summary of the terms that we needed to define, since we are going to come across them as we are going to discuss this topic of kinetics. Of course, we can't finish without mentioning the term acceleration due to gravity. It's an example of the one that, of course, is very common and we can relate to. So acceleration due to gravity is given as g, and this is a constant, of course, whose value is, of course, okay, let's do this. So we said our last definition for a term that we defined was acceleration, which we said is given by the initial a, and it is given by the term g, and this is acceleration due to gravity is a constant which is 9.8. meters per second squared. So in that case, this one means that whenever objects are moving towards the surface of the earth, or maybe they are being thrown up, they'll be subjected to some kind of acceleration, that is acceleration due to gravity. Of course, this acceleration vector is the same on the way up and at the top, and from the top down. So in that case, normally we just denote acceleration giving it a negative value, of course, and that one does not imply, of course, that it's a negative quantity, but the interpretation is that the velocity decreases by that quantity, that is 9.8 meters per second each, meaning that velocity is becoming less positive or more negative when we use this particular sign form, of course, that negative sign. So less positive means slowing down while going up, and the more negative means speeding up while going down. So in that case, the implication of this negative sign means that it is either speeding down or speeding up while moving down, or slowing up while going. An object is slowing down while going up. So in that case, those are some of the terms that we're going to encounter in the concept of kinematics. And I hope we have just had, of course, some information on what they refer to. So in that case, we're going to move on to a different concept that we shall refer to as graphing. So in this case, graphing is a method that we're going to use, of course, in trying to interpret some of the information that we're getting from kinematics. And in a sense, graphing refers to the concept of drawing or maybe tracing on graphs. Now in this case, we are used to the method that uses a two-dimensional space, of course, which we commonly refers to two variables of x and y axis, and this is a Cartesian plane, so we are going to use that when trying to draw our graphs. So if somebody asks what is the definition of a graph, so for us to understand what the concept of graphing is, it's good for us to know what a graph basically means. Now, a graph is a mathematical diagram that shows the relationship between two or more sets of numbers or measurements. So in that case, this is a diagram which is a mathematical diagram that shows the relationship between two or more sets of numbers or measurements. So basically, from the definition, we can see that first it's a diagram that shows the relationship between two sets of numbers or measurements. So this is a relationship that we're going to see, of course, being given in the graphs between numbers and measurements. So in that case, that is a definition of a graph, or we can say that it's a set of all ordered pairs whose coordinates satisfy an equation. It's a set of ordered pairs of numbers or whose coordinates satisfy a given equation. And talking of an equation, of course, we are going to see that these different graphs are going to generate different equations. As we move ahead, we shall see that these graphs that we're going to give are going to generate different sets of equations. And in that case, for us, of course, we have already defined, or I presume that we understand what the term, of course, equation means. Because under that, as I said, we're going to start about, after graphs, we're going to start about equations of motion, of course, which fall under kinematics. Now, in that case, the term equation refers to a statement that two mathematical expressions are equal. So from the term equal, so we can say that it's a statement that two mathematical expressions are equal. So we see an equal sign in between these statements, which we refer to as expressions of motion, of course. So in that case, the graphs are going to assist us to generate these equations of motion. And from that case, we have said that this, of course, is going to entail some kind of expressions. And apart from that, expressions are simply collections of symbols that jointly express quantity. So in that case, from the graphs, this is what we're going to get: equations of motion, which are contain expressions which express, of course, quantity, as we have said. So talking of graphing, the first, we're going to see three sets of graphs, of course. That is an acceleration time graph, which are going to be represented in the format that I talked about, in two-dimensional space. So we shall have that set of graphs, a set of graph, of course. The first one is acceleration time graph. So when I mention about acceleration, it's going to appear in this format. This is the acceleration time. So this time variable will be on this x-axis, and the acceleration will be on the y-axis. So for this case, we have a dependent and independent variables, which we're going to look later. But for this case, we shall just restrict ourselves to the discussion of graphs of kinematics. So in this case, when we talk about acceleration, we say it is the rate of change of velocity over time. So velocity over time is measured in meters, of course, per second. And then acceleration is, okay, no, this is velocity. So this one will be in meters second square, of course. In case of correction, we shall just do that. But time is measured in seconds. So we can just indicate the dimensions or the units, standard units, which are used to measure the specific quantities we have mentioned. So in that case, for acceleration time graph, it represents the change in velocity over time, and the area under the graph is a change in velocity. So in that case, suppose we have a line that is showing motion of a particle, or representing the data for acceleration against time of a particle. And then we have got another one whereby the acceleration is constant. You can see that for the first line, maybe we can denote this one by line A and B, and maybe at this point of origin we write O. So for line OA or AO, we see that the acceleration is changing as time goes by. So which means there's a change in acceleration over time. But for line, let's refer this line to PB, the acceleration is constant, where the time continues to change. So in that case, for this PB, we refer it to as uniform acceleration. This is uniform acceleration, whereas the other one, we refer to it as non-uniform. This is AO, is non-uniform acceleration, implying that the non-uniform is changing with time, where the uniform one does not change with time, it is constant. So in this case, we will see that the area under this graph will represent, of course, the change in velocity. So we can say that, of course, the integral or the total area under this curve represents velocity. We're going to see that one through an equation. So this is for the acceleration time graph. Acceleration time graph for kinematic. Of course, this is graphing. This is acceleration time graph, and we see that whenever we have got this kind of change in velocity, the area under that one represents. Change in acceleration over time. The area under that one represents velocity. Now we have talked about two aspects. That is pp. The line representing pp for a moving object contains uniform acceleration, while this one is non-uniform acceleration. So this is the first graph that we're going to consider when we are going to talk about the aspect of acceleration and time, or maybe the kinematic equations. So we shall look at the second one, which is a velocity time graph. We talked about acceleration time graph, so the second one is velocity time graph. So which means the x-axis will contain time, while the y-axis will contain velocity. This one is time against the velocity. So this one represents the change in velocity over time, and the gradient of the time velocity graph gives acceleration, while the area under the curve gives displacement. So in that case, this is velocity, which is measured in meters per second, and time, this is measured in seconds. And then if we have motion from the original point showing that way, so that one, the area under the curve, so this one is area under curve, represents displacement. So in this case, we are going to have also two sets of velocity, whereby the one that we have already representing can be shown that, of course, this line is, we presume that it is straight. The change in velocity is constant over time, so we refer to this one as uniform acceleration. Acceleration, of course, is given as change in velocity over time. Since the change in velocity over time is uniform, then it is going to be uniform acceleration. Now the gradient or the slope for this kind of velocity time graph gives what we call acceleration. So this is the change in velocity over time. So the gradient gives A. It's just denoted by A. We said A is for acceleration. So the gradient gives A, while the area under the curve gives displacement. So this one is for uniform acceleration. Now the other aspect is for uniform acceleration, of course, which is still under the velocity time graph. Now that one is going to be represented like this. So we shall have x and y axis. Now this is for velocity, and this is for time, and this graph is moving this way. So as we can see that there is the acceleration or the change in velocity over time is not uniform or not constant. Therefore, we refer to this one as non-uniform acceleration. So this is for non-uniform acceleration. And then lastly, we shall look at the time, of course, displacement time graph. So we've moved from acceleration time graph, velocity time graph, and we are trying to see that the constant ones that we are having, the area under the curve for the acceleration time graph gives velocity. For the velocity time graph, the area under the curve for uniform, of course, acceleration gives, of course, we say the displacement. And lastly, we shall look at the displacement time graph. So this is displacement. Number 3, displacement time graph. Now that one is going to be given as this. So this is the y-axis, the x. This is displacement. This one is given in meters, and the time is given in seconds. So in that case, for this graph of displacement over time, presume that this is the origin. The gradient, this is change in displacement, change in displacement over time. The gradient is going to give what we call velocity. So from this, of course, we are going to look at other aspects of all the graphing in kinematics, and we're going to encounter other terms like instantaneous, acceleration, or velocity, which we have not defined. Of course, we can just mention them so that we can be able to discuss them once we come across such an example. So in that case, instantaneous acceleration or velocity, instantaneous acceleration or velocity. Now this one refers to the velocity of an object at a specific point in time, and this one can be found by just trying to do a displacement time graph and then drawing a tangent at the graph at that specific time. So in that case, for instance, we have a graph, for instance, we have a graph of this, which we talked about, which is a graph of displacement against time. And then we can see that the velocity is non-uniform. So maybe we might be required to find the velocity at this point in time. So what we do, we just draw a tangent at this particular point, which is coinciding with that point, and then try to find the gradient of the tangent at that point. So that will be the change in displacement, change in time. So this gradient for this, that is change in displacement. Of course, we know that the gradient is given by the change in y-axis over change in x, and that one gives us m, generally, which refers to the gradient. So the gradient will produce what we call instantaneous velocity. So generally, that is the definition for that. So as I said, these graphs will not be complete without what we call the kinematic equations, which of course we are going to look into shortly. And those ones are going to assist us in trying to, of course, try to quantify, or in any case we come across examples, we are able to evaluate the terms that we have already defined. So in that case, for this one, we shall come to an end of the first discussion of this kinematics. And then the second one is going to entail, of course, the deriving of the kinematic equations, which we have stated, which of course we are going to complement this graphing. So for that case, we will stop there. So thank you guys. Bye. God bless you.